Welcome, guys, to another session on dynamic programming solutions. And today we are tackling problem 6.16 garage sale. This is a little bit involved problem. It's based on traveling salesmen, and we know that that's a complicated problem. So, with that, I guess I'll just caution you to go through this slowly, and you might have to repeat this a couple times to completely understand. I'll try to explain all the nuances in detail. So the problem is that there is n garages in a garage sale, G1 to Gn. The parameters given to us are that there is a gain from going to a garage site, Gj, which is Vj, and you might gain value. Like if you buy some item there, you might be able to sell it for less and therefore gain some value, Vj. The travel cost of going from each garage to each garage is given, and that's Dij. And you're also given from initial point, which we call zero, origin or zero, to any garage. That distance is also given, so you can subtract that as a travel cost. So we are asked to find a subset tour which may or may not involve all the garages and maximize your benefit minus travel cost. Now, we might want to stop here for a moment and think that, okay, this looks like a traveling salesman problem because, in there you have to basically touch every node exactly once, and you might want to be maximizing your return or minimizing your cost or whatever. But that includes all the nodes in the traveling salesman's route. Now, the difference here is that it doesn't say that you have to go through every garage, right? And it's not asking you to do that. It's asking you to find a subset. So the twist is that we have to go through the motions of, the traveling salesman computation. By the end of that, we have to kind of find the maximum benefit or profit across all the possible subsets that you can travel across. And that's where this problem is slightly different from the traveling salesman problem. And we'll show you towards the end how that differs. So with that, let's look at the solution. So before we dive into the equations, let's look at a graphical or pictorial representation of how the solution comes about. So there is an origin, and let's assume that there is a subset of nodes that we're going to go through, and also that the last garage that we will visit is some node j. Okay, and so that kind of is the skeleton of the solution of traveling salesman kind, that you have to think of some garage is the last garage before we return back to the origin. Okay, and then there is a subset of the main set of garages that is sitting here. Okay, so you're going to go from origin to this set um, of garages, and then somehow come out of them and go to this garage J, and that garage J, and then come back to your home. Okay, so that's kind of the basis for the solution, and we're going to define this profit function PSJ, where S is some subset of nodes or garages, and then J is the final node before we head back home. Okay. And keep also in mind that in this PSJ function, we will not consider this leg home. Okay. And you might ask, why would you not consider the leg home? And you will realize that the solutions here, like when the recursion or this equation for reduction is used, it's basically only considering the data from here to this node, and then you'll tack on another node, and then you'll tack on another node. So you never go back. You don't compute the cost of going from this I node going back to the origin. And that's how you're able to tack on more nodes to build this chain. So for the sake of the computation, we will build the equation as this PSJ function as only from origin all the way up to this node J. Okay, we're now going to consider this route back home because that'll come in handy when we compute the final step. Okay, forget this part for now, and this will only come into play towards the end. For now, let's just focus on PSJ, which is the cost of going from origin through this S to this J. Okay, and you have reached J, and that is the function PSJ. So now that we have understood that, let's keep this goal, and the goal is that, over some subset of garages, and let's call this GS, which is some subset of the main garage set, which is G, okay, which includes all G1 to G0 to Gn, whatever, all the nodes are there. And what you have to do is if you're coming from node J, then you have to take this final trip home. And so that distance is dj0. And so you have to subtract that, and that gives you the final cost of the whole tour with this subset GS going through node J, going back home. And so keep that in mind that we have to maximize this. Okay. And so what we have to do as this computation is that we have to compute this partial function, which does not include the trip back home, and which we can use to extend all the problems or reduce the problems here. So keep in mind, if you're going from the empty subset, which is in, that you just go from home to just this node J, this garage J, and then come back home. So then this subset before this becomes empty, okay? And that problem becomes trivial because that's just the value you'd gain from garage J minus, you know, D0J, which is going from here to there. Remember, we are not coming back here in these problems, right? This PSJ is not coming back home. So Vj minus D0J, that can be computed for every node. And then PSJ, remember the PSJ is the function that we're trying to compute, which is from home through this subset S and ending up at J. This is equal to the maximum for every garage I. So you have to now consider not just J, but some penultimate or the previous garage here, which we call I, and we can iterate over all possible I values possible in this subset, right? And so if you iterate over all possible garages by pulling that garage out and then using that as the previous stop. So think of shrinking this cloud just before I, and you can choose any I within this subset. Okay, so you pull that I out. Now the function becomes PS minus GI, and then through I, and then from there, once you have this function, that means that you have value going all the way up to I. So you have a function going all the way up to I. So what is the remaining cost? You have to travel from I to J, so you subtract Dij, and then you'd get, this is actually Vj, and then you're going to gain some profit or value here, which is Vj, and so you're going to add Vj here. Okay, so now that we have understood that this is the equation, just to summarize in terms of this diagram here, what happens is that this PSJ is the function of ending up at garage J, and this function really can be reduced by assuming every possible penultimate or previous node. And if you compute a maximum over every possible node for this subset S, um, and then take a maximum value over those, then you have maximum value of arriving at J, right? That'll give you every possible combination of previous node, assuming that you are ending up at J, every possible combination within this subset. And remember that the way dynamic programming is going to solve this problem is going to start from a very small subset here. And from there, we're going to expand this problem space so that we use bigger subsets and then even bigger subsets and even bigger subsets. So that's how we will solve this problem. So hopefully you understand and appreciate those two parts. That first of all, we're going to drop this whole final solution, which is going back to home. We're not going to think about that for a second. We're only going to think about problem of going from origin all the way up to the last garage. Okay, let's just call that J. So PSJ is our focus in this part. And once you have understood and solved that for every possible subset and every possible J, then we're going to start talking about how we compute this final goal of getting back to home and this final value. Okay. So now, so let's look at how do we look at the initial condition here. And in the initial condition, what happens is that we go from 0 to some garage J and back to home. Okay. And this back to home we will ignore for a second because for this part we're not going to consider this. So the total value is Pj or Vj minus T0 to J, which is going to this garage. Okay, that is the total value in this. And so what this means is that the if you consider only one garage, that is you're going from home to that garage and back home, then the subset that we use here is empty. And so at the end of this initial computation, which is pretty trivial, you would use this empty set. Okay, in this early, very first step, you're going to use the empty set, and you're just going to assume that I'm just going to go through one node, one of the possible nodes, and come back home. Okay, so at the end of this step, very trivially, you have computed this, which is using this formula for any j, and j here is 0 to n, whatever. So you can, I'm sorry, it should really be 1 to n, because 0 is used as like the, the home. So you have basically computed the empty subset, right? And then we're going to build upon this by using a slightly bigger subset and a slightly bigger subset, and that's how the problem will solve itself. So let's move on to the next step. So in this step, now consider a set of one garages, right? So previously we used this empty, and now if we, let's for example, let's say there was G0 in there, right? And then we were going through one final one, which is garage one. Okay, so now if this was something you wanted to compute using this equation, you can obviously break this into, if this was empty, then you would go through empty and zero, and then plus, obviously you have to go to one from zero to one, so minus d01 and then p1. Okay, so that is the overall value because there's only one possibility here. So now what you can do is that you can write down every possible subset here, every possible value here, and that gives you every solution where the subset has only one node in it, right? So you can compute this where S is one garage subset. And you can vary this from all the way from 1 to n. You can vary this from, garage 1 to garage n. And you would have, one garage subset here and every possible final destination. Obviously, you have to eliminate the ones which don't make sense because this one cannot be inside this, right? This one cannot be inside this. So that's an invalid case. So you have to just make sure that those are eliminated and those are not considered. If this is one and this there's a G1 inside, it's meaningless. You could also consider that to be an empty set. Okay. So now that you have understood that, we have now solved this for a set of one garages. Let's move on. So now let's do a set of two garages. So if there was by the same principle, now we can do a set of two garages. And if you do G0, G1, and then going through two, then you can break this down into just go through G0 to 1, and then, just pull this G1 out. And if you pull the G1 out, then this is a problem we have already solved previously, right? G01, because it only has one node here. And so we have solved this problem in the previous slide. And so now all we have to do is take this and go from, because this is ending at 1. Now we go from 1 to 2. So you subtract that, and then you add the value that you will gain at 2. And that's your answer for this. That's one of the answers. And you could pull G0 out. And if you pull G0 out, then G1 stays inside, and then you get from 0 to 2 and then P2. So you take the max of these two, and that becomes the value here. Now you can try every possible two garage subset here and every possible value of the final node, and that gives you this slide. And all possible solutions have been solved. Now the final piece of the equation is that when you keep extending this, you will eventually reach all the nodes. All n nodes in all n garages have been reached. And then if you reach that point, then what you have to do, and you obviously have tried all possible, um, actually, there are not all possible sets because there's only one set. And once you reach that superset, basically it becomes, this S becomes just one value. It's all the garages from 1 to n, right? And then what happens is that if you want to pull some j out from there, then you just pull out one node from there and one penultimate node, one previous node. So if this is j, you're gonna from this s, you're gonna pull out one node at a time. And if you remove that node and compute this, then you can compute this final set, which is all garages in here. This s is g, right? Once you have reached the final value, this s becomes g. And then once you have computed that, then you have computed this PSJ function. Okay. PSJ function is basically um, every possible subset all the way up to G here, and then using some final node and then coming back home. So we have computed all this, right? So now let's look at the order of this PSJ computation. We're not still solving the problem. We're just looking at the the table lookup for this PSJ. And the order is computed as follows. There's how many subsets are there? If you have n elements, there's 2 to the power n subsets, right? Because you can have one, two elements, three elements, four elements, so on. So all possible, um, selections of elements would give you 2 to the n subsets. And you have to remember, we started with the empty, then we had one, then we had two, and so on till we reached all garages. So, so we had to solve all those. Now, the last node can be chosen in order n, and the previous node can be chosen in order n. So at any point, remember that when we go to the next slide, we use the answer from the previous, but there's still iterations, and those iterations were n squared. On every slide, if you go back, you see that in every slide we have solved n squared because you map this to the previous slide solution, but then you do this I and j, right? And because of that, you have to compute it n squared. So the overall complexity of computing this matrix was n squared 2 to the power n. Okay, and so the complexity of this is order n squared 2 to the power n, and that is only for this PSJ function. Now we are ready to talk about the final solution. Remember, the final solution is to compute PGS minus DJ0, which is now we are coming back home, okay, to the origin. And so once we have computed every possible P, S, comma, J, what we can do is that we can start computing this final function, which is coming back home, okay? And so you go through each subset GS. If you're given garage G, um, now compute empty set of one garages, set of two garages, three garages, four garages, all the way up to n garages. So you iterate over all possible subsets of garages and all possible final garage values this J could be. So how many ways can you choose this J? N ways, because there's only n garages. And how many ways you can choose this subset? 2 to the power n, right? So in n times 2 to the power n, and assuming this computation takes us unit time, because this value is known and this is just a subtraction, this value is known. So we can do that in n 2 to the power n. And remember that the previous step of computing this was n squared 2 to the power n. So this is still smaller and we can ignore this. So the final computation of this, we can ignore this value. It's just computing the max over this coming back home value. So overall, the order of this algorithm is n squared 2 to the power n. And that is almost the same. I mean, it is the same as computing for traveling salesman problem, because there, once you've reached the final, if the PG comma J is your answer, right? That's what the answer is. So um, in this case, guys, that is the final solution, and we have essentially solved the garage sale problem by remembering two things. One, you must remember that first you have to solve. Forget about the coming back home part. You just have to solve from origin through some subset to some final node J. Okay, and once you have solved every possible set and every possible node that could end up as the final node, then we are ready to look at this final slide, which is compute the path all the way back home. And all the data is available to you. Every possible subsets available to you, every possible final node is available to you. You just need to plug the answers here and iterate over all this. And then you will get this final answer, which is the journey back home and the maximum value of the journey back home. Okay, so that's it, guys. Thanks for watching this video. Hopefully if you stuck with me for this long, I know this was a long problem and this was a bit complicated. I guess you should probably review the traveling salesman problem that I have also done, and that might help you understand this better. But in general, the idea is pretty simple. You need to find all possible subsets and remember, starting with an empty subset and then building up from there. That's how you build up to the full scale solution where you have n nodes, because you really started with an empty subset and the problem was almost trivial, right? And then you added one more, and then you added one more node. So The solution still takes a lot of time. It's 2 to the power n. It's an exponential algorithm, right? It's 2 to the power n, and so it's an exponential algorithm. It's an expensive algorithm, but still, dynamic programming has solved this. Instead of making it, maybe a factorial problem, it's become a little bit simpler problem. So thanks for watching, and thanks for sticking with me for this long. And hopefully, if you enjoyed the problem, give me a thumbs up or subscribe to my channel. This was the garage sale problem in problem 6.16. And thanks for watching. Until next time, bye bye.